Link0 directives are Gaussian's method for specifying various computer resources that are available to the calculation. Some of the resources that can be specified with Link0 commands include memory, disk space, and CPU resources. This video will discuss specifying each of these items in turn. We will also discuss Gaussian's default.root file for setting system-wide defaults for calculations. Directive names begin with a %, and they are placed before the root section within an input file. GaussView also includes controls to make it easy to specify the most commonly used directives via the Link0 panel within the Gaussian calculation setup dialog. Gaussian 16 needs memory in order to perform its calculations. By default, it allocates 800 megabytes. You can specify a maximum amount for the software to use. You may do so to increase program efficiency. Doing so may also prevent degradation of overall system performance on computers with limited resources. The Link0 command for memory resources is %mem. Its value specifies how much memory, RAM, will be allocated for the calculation. Typically, you specify the desired amount of memory, including the units. In the Gaussian calculation setup dialog, the memory limit item on the Link0 panel performs the same task. You can either select an item from the menu or use the Specify option to enter the desired value and units with the controls that appear. Here, we specify a maximum amount of 3 gigabytes. If you don't know how much memory your computer has available to it, you can use the free command to determine this information. Calculations can often be completed more quickly by using more than one processor or core to perform it. Gaussian includes shared memory parallel capabilities as part of their standard features, with the exception of 32-bit G16W, which is limited to one core. Consult the G16 documentation for a list of job types that can be run in parallel. For best performance and maximum efficiency, it is important to limit Gaussian's CPU use to one thread per physical core. Hyperthreading is a technique offered by modern computers to allow more than one thread to execute simultaneously in each physical core. These multiple threads are also referred to as logical processors. We recommend disabling hyperthreading in the computer BIOS for systems used for Gaussian. The %nproc shared Link0 command specifies the number of processors, cores, to use for the calculation. The default is 1. The GaussView Link0 panel allows you to specify %nproc shared using the Shared Processors dropdown. Here, we allocate 8 cores for our calculation. Finding the number of cores present in your computer is also straightforward. We can list the cores in the system by searching the CPU info file in the /proc tree. The more recent %cpu Link0 command allows you to specify the specific cores on which to run the Gaussian calculation, rather than just the total number of cores to use. It takes a comma-separated list of core numbers and/or core number ranges. The third example illustrates the use of an offset suffix having the form /n, which says to take every nth core from the preceding list. So 0 to 31/2 takes every second core from the range from 0 to 31, meaning cores 0, 2, 4, 6, and so on. Gaussian can also run calculations in parallel across the nodes of a cluster or the computers in a local area network. This requires the optional Lambda product. In a cluster or network parallel calculation, each component process is known as a worker. Workers are specified with the %lambda workers Link0 directive. It takes a list of node names on which to run workers. The example specifies a list containing 2 nodes. The GaussView Link0 panel's Lynda Workers field can also be used to specify this directive. Here, we specify that the calculation will run on 3 nodes: Julia, Michaela, and Grace. Shared memory parallelism and network or cluster parallelism can be combined for a single job. In such cases, multi-core worker processes are executed on multiple nodes with the network or cluster. Setting up this kind of calculation has 2 steps. First, set %CPU correctly for each node in the network or cluster parallel calculation. This must be done before the job is started, using the -c- directive in the Gaussian default.root file on each system. The second step is to specify the list of Lynda workers. This can be done in the input file with the Link0 command or in the default.root file on the master node using the -w- directive. Gaussian uses several intermediate files throughout the execution of a calculation. By default, they are stored in the Gaussian scratch directory, designated by the Gauss_scrdir environment variable, or in the current directory. If no names are specified for these files, they are assigned auto-generated names. Unless you specify otherwise, these intermediate files are deleted at the end of a successful calculation. The most important of these is the checkpoint file, which is a results file that is updated as the job progresses. Once the job completes, this file can be used for results visualization. The checkpoint file is also needed for running follow-on calculations and restarting failed jobs when possible. We recommend always saving and retaining the checkpoint files from your calculations. This is accomplished by assigning the file a name via the %check Link0 command. The value given to this directive minimally includes the file name for the file. The most common practice is to use the same base name as the input file with the extension .chk. GaussView adds such a directive by default to the input files that it generates. Note that you can specify either a plain file name or a full path name to %check. In the first case, the file is placed in the current directory. The GaussView Link0 panel provides controls for specifying the checkpoint file. You can accept the default name or specify a different one using the Specify option on the pop-up menu. We choose to maintain the default name given by GaussView. It is also possible to run calculations starting from the data in previously created checkpoint files. This is accomplished by specifying the existing checkpoint file to %check and including the relevant keywords in the new job's root section. For example, geom equals check, guess equals read. Note that when you use an existing checkpoint file in this way, its original results are overwritten by those from the follow-on job. You can use data from an existing checkpoint file without modifying it by using the %oldCheck directive. This command copies data from an existing checkpoint file for use within the current job without modifying the original file. A different checkpoint file is used for the new job. Here, we use the oldCheck file controls in the Link0 panel. We specify the file as benopt, which refers to the file benopt.chk in the current directory. Both the checkpoint file and the oldCheck file items include a Navigate button to the right of their name fields. Clicking this button would allow us to select an existing checkpoint file using a File Open dialog. Both items also have a Full Path checkbox as the final item in the line. When it is selected and the name field contains only a file name, GaussView will include the entire path to the file within the corresponding Link0 command. When it is unchecked, only the file name is included in the directive, which is what we choose to do here. When the name field includes a directory specification, the setting of full path is ignored. The read-write file is the largest of Gaussian's intermediate files. It has the extension of .rwf. This file is needed for restarting many long-running calculations, including analytic frequencies, coupled cluster calculations, and NMR predictions. You can name this file using the %rwf Link0 command, causing it to be retained after a successful job. GaussView includes a field for it on the Link0 panel of the Gaussian calculations setup dialog. Since intermediate files, and especially the read-write file, can sometimes be very large, combining available space from more than one disk can be helpful on systems with limited disk resources. When the Link0 command's value is a list, the corresponding intermediate file is broken into pieces if necessary. These file segments are stored using each list item in turn. Note that the segments specified in the list should be all located on different physical disks. Each location in the list is followed by a value specifying that segment's maximum size, for example, 4 GB. The special value of -1 can be used for the final item to let Gaussian determine the size. This example shows that the read-write file should use two directory locations, in the SCR1 directory and the SCR2 directory, using the auto-generated name in both cases. The first segment has a maximum size of 1 GB. We can also specify the %rwf directive using GaussView as we do here. The Link0 panel's Edit subpanel displays the Link0 commands that GaussView will generate based on the menu selections. Values that are based on the input file name, such as %check, will contain placeholders rather than the final file name. You can also edit the Link0 directives directly. If you change a value here, the corresponding menu item will also be updated when you return to the Options subpanel. For example, here we change %mem from 3 to 4 GB, and the change transfers back to the Options subpanel. You can also add Link0 commands for which there are not yet GaussView controls, as we'll see later. A complete list of Link0 commands can be found on the Gaussian website. Its link is included at the end of this video. Additionally, we use the Gaussian calculation setup preview panel to view the complete input file, including the Link0 commands. However, they cannot be altered here. Notice the difference between %check, which includes the full path, and %oldcheck, which does not. Gaussian includes a way to provide intuitive names to intermediate files while still deleting them at the end of a successful calculation. The %nosave directive functions as a dividing line within the Link0 file specifications in an input file. Files which are named before it appears, in other words, which are above it in the input file, will be assigned the specified name but will still be deleted if the job succeeds. Files which are named after it, that is, below it, are retained. For example, using these directives, the read-write file and the checkpoint file will both receive the base name Big Job, but only the checkpoint file will be kept for a successful job. The max disk keyword provides a mechanism for telling Gaussian how much disk space is available for the calculation's scratch data. The default is an unlimited amount of space. Max disk is useful for limiting Gaussian's disk use on systems with limited available space. When disk is limited, Gaussian will choose algorithms based on the available space when possible. Note that max disk is a Gaussian keyword, not a Link0 directive. Accordingly, it must be entered into the corresponding field on the General panel of the Gaussian calculation setup dialog. Here, we specify its value as 600 GB. You can find out the amount and locations of free disk space on various computers quite easily. On Linux systems, the df command will display a report for mounted file systems. Gaussian 16 can also take advantage of supported graphics processing units, GPUs, that are present on the computer. Our website contains a detailed discussion of using GPUs with Gaussian, including supported models, determining the GPU resources available, and best practices. Here, we will discuss the Link0 command %GPU-CPU that is used to specify GPU resources. %GPU-CPU's value is the list of GPUs to allocate, then an equals sign, then the list of controlling CPUs. Each GPU requires a dedicated CPU to service it. These CPUs are not available for any other use during the calculation. The controlling CPUs are also included in the list specified to %CPU. These directives do not have items on the Link0 options subpanel, so we must add them manually using the Edit subpanel. Here we specify that all 32 CPUs, cores, are allocated to the Gaussian calculation, which will also use all 6 available GPUs. CPUs 0 and 1 and 16 through 19 will serve as their controlling CPUs. Thus, this calculation will be executed using 26 cores and 6 GPUs. Defaults for the resources specified with Link0 commands can be set in the Gaussian default.root configuration file. It is located in the main Gaussian 16 directory on Linux computers, which is the G16 folder in the location specified as the G16 root environment variable. In GaussView, clicking the Defaults button restores all settings throughout the Gaussian calculation setup dialog to those in the default scheme. Here, doing so changes the root section keywords and clears the additional keywords field. It also restores all Link0 commands to their defaults, which are also taken from the scheme if it specifies them, or more typically from the defaults in the default.root file, as is the case here. The Link0 default root subpanel lists the contents of the system default.root file as well as the path where it is stored. The lines within this file are labeled with a character enclosed between 2 hyphens. For example, -m- specifies the default amount of memory for a calculation. Here, it is set to 6 GB. You may choose to create your own personal default.root file in addition to the system-wide file. It should be placed in the directory from which you launch Gaussian. When there are multiple specifications for the same directive in different locations, such as the default.root file and a Link0 command in the input file, the following order of precedence applies. Link0 directives in the input file override all default.root file entries. Entries in the personal default.root file override ones in the system-wide default.root file. Here is a list of directives that can be set in the default.root file along with the corresponding Link0 commands. Note that max disk would be specified in the first directive, --. We conclude this video with some general recommendations about allocating resources to Gaussian. The size of the job determines the amount of memory that Gaussian will need. For smaller jobs, the default amount will work fine. For jobs on molecules of 50+ atoms and around 500 basis functions, give Gaussian 4 GB of memory per core. If you are using GPUs, more memory is needed because GPUs can only use the amount of memory allocated to its CPU. So if a GPU has 16 GB of memory, you will want the Gaussian calculation to use about 12 GB, so that amount needs to be allocated for each core. For example, on a 24-core system with 2 GPUs, you will need to allocate 288 GB in order to use the GPUs effectively. You should follow the preceding recommendations if it is possible on your system. However, be sure not to allocate so much memory to Gaussian that the overall system is starved, as this will degrade all performance, including Gaussians. As a general guideline, if the total system memory is 32 GB or less, the maximum you should allocate to Gaussian is 50%, in other words, 16 GB. If total system memory is between 32 and 64 GB, you can safely allocate about 2/3 of the total to Gaussian. For systems with more than 64 GB, you can allocate up to about 75% of the total memory. The FreakMem utility will calculate the amount of memory required for Hartree-Fock and DFT frequency calculations. In this example, a calculation involving 250 atoms, 1,000 basis functions, and a basis set including F functions will need about 6 GB per core. In allocating disk space, it is generally recommended to set the max disk to the amount of available space. Also, if you are using post-SCF methods, such as MP2 or CCSD, be aware that having more memory will reduce the disk use. The specific formula for eliminating disk I/O and CCSD calculations is given here. Solid-state disks can also greatly speed up disk I/O. SSDs are 3 to 5 times faster than high-performance disk drives, at 8 to 10 times the price. SSDs also have much smaller capacities. An SSD can be useful for Gaussian calculations when I/O is the limiting resource. In practice, this means that an SSD will give little improvement for DFT calculations as they are CPU and/or memory limited. In contrast, for I/O-intensive post-SCF methods, an SSD for scratch will make the jobs run significantly faster, provided the SSD is large enough for the calculation requirements. The required disk space varies depending on the method used. You can estimate the amount needed by scaling up from a small job using the factor that is appropriate for your method. Note that the Gaussian output file lists the size of the read-write file at the end of the output. Additional information about the topics we have considered here is available on our website.